Hey, welcome everybody into the Wells Tech Garage for this week's episode of CounterPoint. Now, for those of you guys that saw the video from last week, we had a part 1 and a part 2 of this wiring connection, current draw, what is the best way to connect our wires type of video. Now, after the first and second videos, you guys left a ton of comments on these things about different things that you would maybe do differently for this test. And you know, we really didn't see much corrosion across these 10 connections on here, but the one thing that I heard pretty much synonymous across all the comments was we should be increasing the load across the connections. So what I've gone out today to do is do exactly that. So you can see we got 5 bulbs wired up here, and then we also have a main headlight bulb. Okay, so we're going to draw each of these as roughly an amp, and that headlight bulb is roughly 6 amps of draw. So we should be pulling roughly 11 amps through this circuit through each of our connections that were in the salt tank. Now what we're going to do is I'm going to set this up to run just the headlamp, just this single headlamp, and then the headlamp and the 5 bulbs together. So we're going to do a minute with the headlamp and a minute with the other bulbs, and then or both together, and then we will review and see what they've got for each connection. Over here on the left, we got 2 meters set up. This one's going to be measuring current on the circuit, and this one is going to be measuring voltage drop. So you can see right now I have the power supply turned on, and it's measuring charging system voltage currently. All right, so as soon as we hook up, this is our control wire. As soon as we hook up, there we go, we're dropping roughly 0.75 or 750 millivolt, 75 millivolts across the connection from battery positive to the connection. And then you can see we're pulling roughly, if we move the decimal point, 5.85 amps. And if we go ahead and we plug in the other 5 lights as well, our voltage drop goes up. Now we're dropping 142 millivolts, and you can see our current draw is now roughly about 11.58. So across our known good, untampered with wire, we're good to go. You guys can see I have the thermal camera set up. Now, before we get to doing the experiment, I just want to show, I found this out on the internet. This is an engineeringtoolbox.com. They had a really nice wire gauge layout. I'm currently using 16 gauge wire for everything, positive and negative leads. And it shows here that we should be pulling about this much amperage depending on the amount of cores in our wire for 16 gauge. So at 11 amps, we are definitely stressing this wire, and that's great. We want to kind of stress test this and see how it goes. So I guess without further ado, we'll fire up the stopwatch here, get that ready to go, and we'll start for 1 minute on just the headlamp. Actually, let's make sure we turn the thermal on, and we'll bring that up full screen. All right, here we go. This is just the headlamp. And start. Okay, so after a minute, we don't see really any change in our wiring on our control wire. It's warmed up a little bit. The entire wire is warmed up a little bit. No noticeable change across our voltage drop, our amperage draw, or our heat across the wire. Now let's turn on our other 5 bulbs, and let's start this again. Okay, so after another minute, you can definitely tell that our wiring has definitely increased in temperatures up to 85 degrees. We're definitely stressing this 16 gauge wire without any sort of connection in it, just by running these 11 amps through there, 11.5 amps through there. All right, we'll go ahead and disconnect this, and let's go on to the next one. Now I think next what we'll do is we will start with known good. We're going to work the opposite way we did last time. So we're going to start with what I think to be the best connection, solder and heat shrink. Oh, gotta get it in here the right way. You can see the solder and heat shrink right across the middle there. And again, we're going to run 1 minute on the 5 amp load and then 1 minute on the 11 amp load. All right, so we have an 80 milliamp draw. Again, 5 point some amps, and let's go ahead and run a minute. Okay, so after a minute on there, we definitely have some more heating up of the wire, but nothing too serious. So let's go ahead and hook up our other ones. 154, 153 millivolt drop, so really nothing too significant over the control wire. And here we go, we'll start up another minute. Okay, so definitely some significant heating again in our 16 gauge wire, but really nothing that's really standing out right now. This looks pretty normal in comparison to the control. So our solder with heat shrink on it is looking good. Now let's go to the solder with the taped connection. And again, this is the quality electrical tape over this, but it is only taped. There's no heat shrink on this one at all. And let's just turn on the 5 amp or 6 amp load. So, wow, that looks good. A nice secure connection on there. 70 milliamp draw. Let's go ahead and start this up. Okay, so once again, nothing too significant. We're noticing a little bit more warming here. Let's bump it up to the 11 volts. Or excuse me, 11 amps, and start it up. Okay, so after 2 minutes total hooked up, it does look like our hottest spot here is right across the center of this connection, right where our connection is on this thing. You can definitely see that here. Let's So you can definitely see that's where our connection is. So definitely our hottest spot right there. So we are noticing a little bit of temperature increase on this one across the taped up connection. All right, let's swap this out. Now we're going to go with the, this one is heat shrink with a crimped connection in the center. All right, we're looking at a 67 millivolt drop. Start it up, here we go. All right, this is looking pretty good so far. Let's add to it. Pretty nice voltage drop in this one, only 129 millivolts. And you gotta remember, we're stressing the wire on here. So it's more than we would normally wanna see. But because we are stressing the wire, it is likely we'll see more voltage drop. There we go, we're starting to see some change. All right, so again, we have some heat across our connection, nothing too crazy here, but it is right across our connection there. So this one does look okay. All right, up next we're going to do the heat shrinkable butt connector. This is the properly crimped one. The one after this will be the improperly crimped. All righty. Looking at a little bit higher voltage drop this time. Start it up. All right, that's looking pretty normal so far. Nothing out of the ordinary so far from what we've seen. Let's add up and start it back up. All right, so after 2 minutes with our heat shrinkable butt connector, you can definitely tell we have a hot spot in here. I think this is the hottest one yet. Now, I know you guys are probably going to be commenting out there saying, we should run this for longer, we should let it sit for 5 minutes or 10 minutes or whatever it might be. That's probably true. To reach failure point or reach critical temperature or the highest temperature that the wire is going to achieve will probably take longer than a minute. But I'm thinking once we get to the end of these connections here, we're going to really notice a difference in just a minute's worth of time. The goal here isn't to take up a ton of time. The goal is to show the difference in the different connections and why in just a short amount of time it's causing a problem. So if we can show an issue in 1 minute of current passing through it, you're definitely going to have big issues on your vehicle if that's running all the time. All right, up next is our improperly done heat shrinkable butt connector. Again, this is the one where I actually pierced the plastic insulation with the crimper. Looks like a pretty normal voltage drop. Our current looks normal. Let's go ahead and start it up. All right, nothing too serious so far. Looks pretty good. This might be one of those connections that's going to have to spend more time in the salt tank to show us an issue. But let's go ahead and hook this up and fire it back up. Okay, so nothing too serious across this. It looks pretty normal. And if you guys are wondering why the heat trace looks like it's off of the conductor, like it's off the wire here, that's just a calibration with the camera. You can see that it's constantly calibrating. Basically what this FLIR C3 camera that I'm using is doing is it's capturing a thermal image and a digital image, and it's layering them on top of each other. So I'm able to go like this, or if I were to take a picture, I can use the digital camera, or I can use the thermal camera. Okay, so that's why it looks like our heat is actually off of the wire, but trust me, it is definitely on the wire. So our heat shrinkable butt connector doesn't look that bad, improperly done, but like I said, I have a feeling this is going to be one of those that really acts up after it's been sitting for the winter on my truck. All right, up next I think is where it's going to start to get interesting. Next we have the, let's go with the non-heat shrinkable butt connector that we saw some corrosion on already. Let's see what we got with this one. Oh, got to install it the right way. Pretty decent voltage drop. We'll see what it does for temperature. Here we go. Okay, so we can definitely see a significant amount of heat building up here, more so than the rest of our connections so far. Our voltage drop and amperage draw still look okay, but this is definitely more heat in the connection piece on our wire as compared to the rest of the conductor here. So I think what we'll see is a significant increase as we up our amperage here. Okay, so after just 2 minutes, you can already see that this connection is heating up more than all of our other, let's call them more known good connections. I guess this would be the first, well, the improperly crimped butt connector would have been the first, but this is our first connection that we kind of had thought we were going to be able to see fail, and I would say that this is failing. We've only been running this on a high load for 2 minutes, and it's already significantly hotter than the conductor around it. Our connection right now is the weak spot. This will cause failure in the future. So I think this proves that a non-heat shrinkable butt connector does not belong on our cars. And again, that's only after 1 week in the corrosion in the salt tank and 2 minutes of amperage draw through it. All right, so now we have an unprotected connector. This was soldered with a crimpable style butt connector that was only applied solder but had no heat shrink over the top. So let's see how this one does. Our voltage drop looks pretty good. Let's start it up and see what our temperature does. Okay, so nothing too serious on this connection under the 6 or almost 6 amp draw. And I think what this goes to show is that this is a good connection. Soldering a crimpable connector onto the wire to connect two pieces of wire, I think is a good connection. I just think that we haven't had it in the salt tank or on the road long enough to show that corrosion causing adverse effects to our connection. So I think soldering a soldering a crimp connector and then applying heat shrink over it, I think is a great connection to the wires. It seems to be doing okay so far. Let's see how it does under the high amp draw. Okay, nothing too crazy here. I wouldn't say that this connection area is really any different than the rest of the conductor at this point. But again, this is probably going to be one that will be significantly different come spring when we do this again. Because right now, it's not really all that corroded. I have a feeling come spring, it's going to be obvious that we're going to have an issue. All right, so on to the last two. These are the two that we've been waiting for, or at least that I've been waiting for, the wire nut and the twisted pair of wires. So we'll start with the old wire nut. This wire just feels crunchy as I'm moving it. All right, what do we got? Ooh, significantly higher voltage drop. We're sitting at 106 millivolts. Let's go ahead and start up our timer. Okay, so after a minute, you can definitely tell that the conductor or the wire is heating up, especially in this area here. I think what's causing this is the fact that the wire itself was not protected because the wire nut wasn't protecting it, and the salt water wicked its way in. Like I said, when I'm moving that around, it almost feels like it's crunchy. It's already looking like this one is getting warmer than any of our other connections. Let's see what happens when we apply more load. Okay, so after only 2 minutes, you can definitely tell we have red happening up here. We're in the 90+ degree mark here up in our wire nut. We have 178 millivolts of voltage drop. The wire nut is failing us after 2 minutes. We are significantly warmer, especially in the conductor, than we have before. This area in here, in our wire, where I said it felt crunchy, we have corrosion happening. I believe this is only going to continue to get worse. You can see we got a hot spot right here as well. So our wire nut, for those of you who said, hey, you know, the wire nut passed the 1 amp draw test, sure, it might have passed the 1 amp draw test for that time, but under 11 amps it is definitely failing, and it's only going to continue to get worse because it has no protection in the circuit. Okay, let's move on to the last one. This one is going to be the one that is going to show us something, I think, because this showed us a problem under 1 amp of draw. This is our twisted connection, our twisted and taped pair of wires. Let's see what we've got. So again, we'll start with just our 6 amp draw. And look at that, 500 milliamp draw across the circuit. Let's go ahead and start up the timer and see what happens here. We're already seeing significant heat across our twisted pair there, and we're only not even 10 seconds in. All right, so after a minute, you can definitely tell we have a significant temperature increase over anything else that we've looked at before. 132 degrees here, guys. This is a failing connection. Hopefully we don't have any smoke coming out of this thing. Hopefully I don't have to go running for a fire extinguisher, but let's go ahead and up our load and see what happens after another minute. You can definitely tell our amperage is significantly lower, right, because our resistance is higher, Ohm's law. Resistance went up, voltage remained the same, amperage goes down. So we're at just under half of a volt of voltage drop, just over half a volt, almost 0.6 of a volt of voltage drop. And look at this, guys, we're 160, 165. This is a failing connection. I wonder at what temperature this tape starts to melt. We're 30 seconds in. $177, 8, 9, 180. So needless to say, this is a bad connection. Never, ever, ever, ever twist wires together and connect them with electrical tape. This will eventually start a fire, a thermal event. I've been to some training before where they couldn't say that it would start a fire and they called it a thermal event. So we're up over 200 degrees across this connector right now. I'm going to turn off our lock on our temperature scaling and just see what this looks like under appropriate scaling. 212. It's still climbing, guys. I don't see any smoke yet, but I have a feeling we will soon. Look at our voltage drop is increasing, right? Heat equals resistance. Ohm's law, well, I guess it's not really Ohm's law, but Ohm's law says with resistance comes a lower current. So we're at 1.121, and our voltage drop continues to climb. We're dropping voltage because our resistance is going up. 235 degrees. So, without a doubt, guys, our wire nut is failing and our twisted pair of wires is failing. Everything else right now seems to be passing. But again, we're going to do this in the spring after these have been sitting underneath my truck for a significant amount of time, roughly 3 months or so. We're going to do a part 4. But this is a pretty good test to show, for the very least, that these two types of connections are not going to do us any good. We're at 245 degrees across this connection right now. This thing is probably going to start smoking soon. Our other connections all seem to be okay. So I guess to sum it up, guys, there's a lot of other things that we can do here and a lot of other factors that aren't being applied to our experiment here. Heat cycling, vibration, electrolysis. There's a lot of comments that you guys brought up to do things differently, and I agree. There's a lot of different things that we could do here to promote the exact best experiment to something that you would see on the vehicle. And that's what we want to try to base our tests off of, is something that would be real world. But really, guys, I think this proves a point of what kind of connections we should be using and which we shouldn't. And we'll really see again once spring rolls around. Now, these wires will be sitting underneath the vehicle for roughly 3 months in a Wisconsin winter. They will not be connected to anything, so there will be no current flowing through them. So there will be no electrolysis on here, but they will be going over bumps and everything else, so there will be some vibration to them. It's not going to be any sort of value that I can give you. It's not going to be anything quantifiable, but there will be vibration. There will be heat cycling because it is going to be driven in the cold. It's going to sit in my garage, so there will be some heat cycling, but there will be no current flow on this wire, so we will not see any sort of effect of electrolysis on our connections. So, all right, looks like our temperature is actually starting to drop off. Now we're at 215 degrees. Seems to be dropping slightly. It seems to be that's where our happy point is. I'm going to go ahead and disconnect this. Ooh, it's warm even at this connection right in here. All right, guys, so that's going to sum it up for today. I hope anybody who thought they could still use wire nuts in a car or was still twisting wires and taping them, I hope this goes out to show you that you can't. You need to be using these other connections. And really, guys, you can see how hot the conductor is in here. When we have a corrosion issue like this, it's going to cause the rest of our conductor to heat up as well. So if you're running into repeated failure of switches or something like that, check out the load in the circuit, whether it's a wiper motor or a blower motor or something like that. That could draw excessive load, which is going to heat up the conductor and cause issues. So to sum it all up, guys, don't use wire nuts, don't use twisted pair of wires with electrical tape over it because it will fail. This could potentially cause a fire under the dash, just like the story I told of that Toyota that I had come in when I was just starting out. It caused a fire. A twisted pair of wires caused a fire. So we have to be connecting wires properly and appropriately. And I think that's about it, guys. So if you liked what you see, please give us a thumbs up. Please subscribe to the channel so you can check out more of our awesome videos. If you haven't caught part 1 and part 2, make sure to go back and check those out where I go over each connection, show you guys how to connect them up, and then have them all wired up together. So, all right. Happy Thanksgiving, guys, and we'll see you guys all out here again for the next episode of CounterPoint and for the next live broadcast we have coming out. So thanks for sticking with me, guys. I hope you enjoyed this. We'll see you next time. Happy wrenching, everyone. Thank you.